Alright, so I'm going to try to add sound to this video here. At this point I've already prayed and found some markers. Now I'm going to start the work. So this is lecture 4, part 1 of my advanced calculus lecture set from 2015, the fall. When I originally took this video, unfortunately the mic wasn't plugged in or something, which is most unfortunate because I'm fond of this particular lecture. Anyway, so here what I'm about to do is to prove a product rule. Here W1 and W2 are in fact normed linear spaces, and W is another normed linear space, although often W would just be the reals or the complexes or R3 in typical applications, and W1 and W2 would often be like R3, both of them, or things like that. So this particular product rule I'm about to prove will include the way the dot product behaves, the cross product, matrix multiplication, scalar multiplication, many things. Anyway, so these are the properties. We're assuming distributive property both sides for this bilinear function. I would say it's an algebra, but you know, the beginning and the ending aren't necessarily the same. Even both slots don't have to be from the same. As long as it's got this bilinearity, we're going to be able to express the star product in a uniform way, which allows us to just say a general calculus rule for it, as we'll see going on here. Man, I wish I could remember what I was saying. Oh well. The children are restless. They will become louder as this video goes on. I'm sorry about that, but it is the case. Let's see here. What have I remembered? What have I forgot? Uh-oh, somebody broke something. Sadness. Alright, anyway. Claim. Now this notation, d sub a of f1, f2, I'm saying the differential, alright, of the function. Now in the previous lecture we've already defined what it means, what a differential is, alright, in terms of the Fouché derivative. It is the best linear approximation to the change of the function at that point. And so here what I'm saying is the best linear approximation to the change in the product of f1 and f2 is given by this linear combination of the products of the differential with the function. It's a sort of generalized product rule, or Leibniz rule if you prefer. And now I'm explaining what this compact notation really means. It means that if you are at the point A and you act on H, you get dAf1 of H times f2 of A plus f1 of A product with the differential of f2 at A acting on H, like so. So that's the claim. Now this isn't currently in my notes, by the way, either, and one of the things I'm trying to do in this particular offering of advanced calculus is to elevate results to normed linear spaces, whereas my previous versions of advanced calc notes only have for Rn to some extent. And this is a work in progress, of course, but ultimately I'd like to get the first few lectures in advanced calculus done at the level of normed linear spaces, because that will subsume all of the typical examples and also give us a good exercise in abstraction. Alright, so yeah, I better assume that f1 and f2 are differentiable at A, otherwise this is just total nonsense. So if I do assume that, though, what can I do? What else can I say? Oh, okay, so in fact the domains of these functions doesn't even involve W1 and W2. It could be from some normed linear space, basically V. But we of course would want F1 and F2 to have a common domain. At least that's the generality I'm going for. I guess you could probably abstract this further, but that'll suffice for our purposes. So V is another normed linear space on which we have a notion of distance, since we have a norm and we can calculate limits and such, and consequently the Fauché derivative. All right. What we got here? All right. So the bilinearity of the product, but what that essentially means is that there exist, you might call them structure constants, although that typically has a more precise and technical meaning. But there have to exist constants, real constants, such that you can write the star product of F1 and F2 just in terms of the component functions of F1 and F2 and some set of constants Cij, Now this epsilon sub k is my current notation for the basis of the, oh no, this is before I found out about the autofocus. Stupid thing, if you don't set the manual, if you don't set the focus range to a particular thing, it'll do this sporadically. Whoa, whoa, man, it makes me sick. Anyway, these things, excuse me, these are just the basis for the W space. We said W1 and W2. The product of W1 and W2 elements gives us something in W, and my epsilon sub k are just a basis for that. The Cijk again are real numbers. Those would be different things according to different products. Like, for example, if you're dealing with a dot product, then W would just be the reals. This epsilon sub k drops out. It's just the number 1. And so it'd be like Cij, the k isn't necessary if we're dealing with the range being the reals. So like the Cijk just becomes Kronecker delta ij, provided we're using we're talking about Rn and the dot product. Alright, so notation. Yeah, the span epsilon 1 through epsilon dimension of W, that's the range for the product, you will. We also will need, so that the basis beta 1 through V1 through Vn, that should be the basis for the range of F1, and that's the basis, beta 2 is the basis for the range of F2. I should say the domain has yet another basis, which I don't know if we need to get into just yet. All in good time. We'll end up taking partial derivatives with respect to the domain basis, so at some point I'll realize I need to introduce that too. Not there yet. So here I'm just explaining what the notation F1i means and F2j means. Those are the component functions of F1 and F2 with respect to the basis beta 1 and beta 2 respective. So these F1i and F2 upper j, those are in fact functions, real valued functions, from V to the real, well, like I said, real valued functions, or real valued functions from V to the reals. I think this is all being done at a point. I should say you could say that the function's defined in some neighborhood of the point A around which we're differentiating. Oh, this is exciting. What am I going to define? What do we got here? Oh, I think, come on, Belu, or whoever it is. Oh, whose fault was this? Who didn't turn in this mic to plug in my mic today? I will not name names. You know who you are. Anyway, over here I have written Vi star Vj is Cijk, epsilon k. It's kind of a weird product because this is from W1, this is from W2. And, oh, come on, pan over, dude. Come on, man, you're killing me. Pan. Arrgh. Again, if you could see it, it would just be Cij epsilon k summed over k. That's how you could take as a definition for these structure constants if you wish. And again, it could be dot product, could be cross product, could be matrix multiplication, could be a product in an algebra that you're less familiar with. There's all kinds of things which satisfy that basic bilinearity that we studied at the start of this. So this is a very general product rule that I'm proving here. Eventually. I'm going to get to it. Come on, man. Get to it. What am I doing? Where'd I go? Come on. Oh, there we go. Man, I wish I could find those notes. I found my second folder in advanced calculus from that year, but I can't find the first one at this point. Somewhere here. All right. So the partial derivative of f1 times f2 with respect to the lth coordinate in the domain. All right. So I'm a little rusty here. I can't remember if I've defined partial derivative before or not in this series of lectures. If I haven't, the partial derivative would just be the directional derivative in the direction of the lth basis vector in the domain. So here I'm just trying to face the music. What is it we're going to have to differentiate? And how do you partial differentiate a vector valued function? Well, you differentiate the one component at a time. I think we're really working on proving that. Not here precisely. But. Okay, so actually the argument is this right now. This is an observation, right? So that's actually the component function of f1 star f2. So I'm going to propose, basically, I mean, this is kind of a backwards argument. What I'm doing is I'm working out from consistence, from just ordinary the partial derivative operator has just ordinary Leibniz rule at the level of products of real functions, right? And so because of that, I will get this. So you might prove an exercise, which is that the partial derivative of a real product gives you this product rule. That's essentially just calculus 3. Maybe I need to make a homework problem there, though, for next time I teach this course. Anyway, that said, so what I'm trying to do is work out the derivative of the component function. This epsilon k is just riding along, and so I'm looking at I'm just differentiating this formula, and then I'm going to try to identify what is it in terms of star products. It's almost there. I mean, basically, if you just distribute, the next thing I'm going to do is hopefully I'm going to distribute this through there and write it as two sums, and the things we're trying to work out to will follow. So in other words, the claim really follows from a lemma, which is that the partial differentiation of a component function, all right, obeys the usual rules for real products. In other words, the big product rule I'm proving here is really a simple, straightforward consequence of the ordinary product rule for real valued functions of real variable. Which isn't terribly surprising. That's always what happens when you actually do specific proofs for the product rule for the dot product or the cross product or matrix multiplication or whatever else. You just have to be careful not to reorder the product, because usually we don't have commutativity of the product. So the Leibniz rule that we sometimes teach Calculus 1 students will fail us. We can't always put the derivative first or something, or second. We can't do fg prime plus gf prime, or excuse me, fg prime plus gf prime, or we can't do f prime g plus g prime f. Like, that won't work. You're going to have to keep them in order. Now here I'm finally getting around to this is something, so here I'm actually using something I proved in the next lecture, honestly, which is that if you have continuity, I mean, this is the connection between the derivative, the differential rather, and the partial derivatives. If you have partial derivatives which exist and are continuous, we'll prove in the next lecture that you actually get differentiability, and in this way. The converse, unfortunately, is more subtle. If you have differentiability, it doesn't automatically imply that the partial derivatives are continuous, but that's a more subtle point, which I think I'll start to talk about later in this lecture. What's over here, of course, is just the same thing, but with, hey, actual panning, yay. Oh, look, there's that thing I talked about earlier. What we got here? I think breakfast is upon us. Let's see here. Right. So I'm just using this connection between the partial derivatives and the differential if it exists, and is is, if these are continuous and exist, then they will provide differentiability in this way. Now I'm assuming that f1 is differentiable at a, so this isn't like a big deal. I mean, there's nothing. It's actually, I don't even need that big theorem to do this here. I mean, there's just, this is the relation between the differential and the partial derivatives. In the case that it is differentiable, you can rewrite the differential in terms of a linear combination of partial derivatives in that way. That follows straight away from the linearity property of the differential, and the fact that partial f1 partial xl is really just daf1 of, let's say, I don't think I have a notation for it here, but the elf basis coordinate, elf basis vector in the domain, the v. Most things I'm doing on this here are in either w1 or w2 or w, so the v is implicitly appearing through the partial derivative with respect to xl. All right. All right. Yeah. Again, as you're following along in the notes, remember section 3.1 of my notes currently, the 2015 version at least. 3.1, I define the derivative with respect to a normed linear space, but then if you look at like 3.2, 3.3, 3.4, most of my proofs that I have typed out are for the case of real valued function. I mean, like from Rm to Rn, but you should understand I'm trying to elevate those proofs to normed linear spaces, and here's one of the places where actually, this includes the proof of about 2 or 3 different things in my notes. I have separate proofs, I believe, of the product rule, the scalar multiple of a function times a vector valued function, the cross product, and the dot product. I think those are all separately proved in my notes. If not the 2015 version, certainly previous versions, but yeah. Now, if I recall correctly, after I'm done with all this, I will carefully define the partial derivative with respect to xl, which is maybe a bit cart after the horse or whatever, but maybe before the horse. The cart should be after the horse. In typical travel, at least, yes. Alright, come on. What's my point? probably talking about different cases. This covers dot product, cross product, matrix multiplication. Remember, the set of matrices is a normed linear space. Some of our more fun homework problems come from that. The children are restless. Alright, come on, get on with it. Sorry, I have not added more exciting audio. Come on. I'm afraid to fast forward on the YouTube right now because where this computer is, the internet's kind of sketchy and it could put us in the circle wheel of death for a while if I'm not careful. I must be apologizing for whatever it is I put out of order here. Come on. Erase it already? Am I going to erase it? I'm going to erase it, aren't I? Jump ahead a bit. Oh, yeah, I am erasing it. Alright. Alright. What's next? What's next? Alright, we'll pick up again right here. This is probably where I will explain what it is I'm jumping over. But the children are upon us.